Hello, welcome to this video presentation about the Smart Electric Meter, which is the group project that we've decided to pursue by Group 4. This group is composed by Boris Navarro and myself, Carlos Carros. We are from Florida International University, and the course is Microcontrollers for IoT. The course code is CNT 3142. To begin with, I would like to go over the creative process of deciding to create this product. The main objective of this project is to design and develop a smart energy meter that can monitor electricity consumption in real time and provide remote access to this data through IoT technology. When the team was discussing ideas on which of them to pursue, the concern of electric waste overlapped as well as the great feeling of uncertainty because in the modern era, the amount of electrical gadgets that become part of most people's day-to-day is never ending. So it's just more devices and more devices being connected to the same circuit. So we wanted to resolve electrical work around the house while reducing electrical waste. Neither of us have experience with AC before, but we knew that a simple multimeter would not do the job because beyond just measuring values, we decided to create a logger and visuals to improve the overall experience. By doing this, we would create a window that can allow anyone that uses it to see the power draw without the need of using probes or being near the measured component at all. To begin with, I would like to go over the components that we use to make this idea a reality. So, the core components are the Arduino Mega, of course, that will act as the brain of the project. It will read the data from the voltage sensor and the current sensor, process it, and then output it to the LCD display and to the Wi-Fi through the ESP8266. Now that we're talking about the sensors, we have the ZMPT101B, which is the voltage sensor. This one measures the AC voltage from the grid safely, and it outputs a low voltage signal proportional to the actual AC voltage, making it readable by the Arduino. We also have the current sensor, the SCT013. This one measures AC current using a clamp, which is non-invasive, and it gives the current flowing through the wire without cutting it. Now, this component requires supporting components. The first one is going to be a 10 nanofarad capacitor. This one filters the signal to smooth out the noise from the sensor before it's read by the Arduino. We also have a 100 ohm resistor, which will work as a button resistor. This one converts the SCT013's output current into a readable voltage signal. And lastly, we have a voltage divider composed of two 10k ohm resistors. This basically centers out the AC signal around the 2.5 voltages, which is half of 5 volts, so the Arduino can read both the positive and the negative parts of the AC waveform without damaging it. We also have the display and monitoring. So we have the LCD display, which is a 16 by 2 that has a 10k ohm potentiometer just to change the contrast on the text and make it more readable. We have the Wi-Fi login by the ESP8266 ESP01, which just sends the sensor data to the internet. We use it for remote logging. Actually, we use it for remote monitoring and logging through ThinkSpeak. And lastly, for connectivity, we're just using DuPont wires. Now, in this first section, we're going to just go over the highlights of the code. We're setting up the foundation of our energy meter system. Let me walk you through what each line of code does. We start by defining calibration values. These are crucial for accuracy. The volt call value of 97.837 is a specific calibration factor we determine for our voltage sensor to ensure accurate readings. Similarly, current calm at 0.567 is calibrated for our SCT013 current transformer. Then we assign analog pins A1 for voltage measurement and A0 for current measurement. These pins will receive the analog signals from our sensors. Next, we create an instance of the energy monitor class from the emonlib library, which handles the complex calculations needed for energy measurement. And finally, we initialize our key variables: current, voltage, which a default of 120 volts for US mains, power, and energy in kilowatt hours. These variables will store our measured values throughout the program's execution. This short but critical section initializes our energy monitor functioning. The first line configures voltage measurements, taking three parameters: the analog pin we're reading from, our calibration factor, and the phase shift value of 1.7. Set phase shift is particularly important because it compensates for the timing differences between voltage and current waveforms in AC circuits. The second line configures current measurement with the pin and calibration factor we defined earlier. These two lines establish our system and how it will accurately sample and interpret the electrical signals from our sensors. Getting these settings right is essential for accurate power calculations. Now, continuing with the previous slide, what we're seeing on screen is the heart of our energy meter's functionality. Let me explain what's happening. The first line calls the calc_vi function, which samples both voltage and current simultaneously. The parameters 20 and 2000 tell the function to sample 20 half wavelengths with a timeout of 2000 milliseconds. This sampling allows us to calculate true root mean square values rather than simple averages, which is essential for accurate AC power measurement. After calculation, we extract several key values. We have IRMS, which is the root mean square current, which represents the effective current in an AC circuit. We have VRMS, which is the root mean square voltage. We have the apparent power. This is the product of voltage and current, measured in volt amperes. We have the power factor, which is basically the ratio of real power to apparent power, which tells us how effectively power is being used. The final section is where we calculate cumulative energy consumption. We get the current time in milliseconds, then multiply the power by the time elapsed since our last measurement, and divide it by the amount seen on screen, which is 3.6 times 10 to the 8th to convert watt milliseconds to kilowatt hours. This accumulates over time to give us total energy usage. And lastly, I would like to mention that this time-based integration of power is exactly how utility companies measure your electricity usage, making our device function like a professional energy meter.
Here is the schematics for the entire project. It is hard, to explain it from here, but I hope, or we hope, that this schematics is, it is self-explanatory, and we just hope that it helps those interested in creating a similar project use it, and I hope it's useful. Definitely, if they can improve it, they're more than welcome to do so. And here we have the electrical wiring for our project. We have the LCD display, as we mentioned before, the potentiometer, the ESP01 connected, all these connected to our Arduino Mega 2560. We also have the voltage sensor, the current sensor, and all the resistors and a capacitor. I just wanted to point out that here is our extension cord that ends at the power outlet that you see there, and it ends, which is connected to the load later on. Just to point out, let me highlight this: the electrical, the wire that goes through the current sensor has to be the positive wire. So if you ever see any readings that are kind of off, even when you did some sort of when you used our calibration values, you may want to change the clamp to the other wire, just in case you're using the wrong one. Below, you can see that in this next picture, you can see how we actually did that. We took the computer power cord, cut it in half, then connect two wires to the voltage sensor. We put them all together using wire nuts. Then we clamp the current sensor to one of the wires, as I said before, to the positive side. Now you may wonder how do I know? Is it just like clamping in there? Well, not exactly. You have to look at the top of the sensor to show you the direction of the flow of the current, right? So it is indicated by an arrow, as you can see in this next picture. Okay, for our project, we will be using these treadmill as a load. We're using the current sensor, as we mentioned earlier, the voltage divider, all this connected through the power cord created from a the desktop power cord, our Arduino Mega, potentiometer, the resistors, and the ESP31 for our connection to the web server. At the end of the cord, you have a power outlet, which will be used for the connection. Now we have the display, LCD display, showing all the values collected. At this point, it's pretty much 0. But since we have had this connected for a little while, we already have some data collected on the website. We're using ThinkSpeak for collecting data, and as you can see, it's cumulative, like the graph keeps going up. Now let's connect it and see what happens. As you can see, we already have power, 9 watt. Current, we already have it at 0.5 amps, 0.4 amps, and the energy consumption at 0.09 kilowatts per hour. If you look at the graph, if you look closer, we can see that the number starts going up. It has like a 15-second delay to update it on the website. So every 15 seconds, we can see an update of the values. Hope you can see that clear now. Now, it is just turned on. It is not actually working. Now when we turn it on and the treadmill starts moving, you see the numbers at 16 watt and the current at 0.8 amps. Consumption 0.010 kilowatts per hour, and you see the current reached 1 amp already. 21 watts, 1.1. And you see already the graph going up, all the way up. You can see the gadgets showing same values. Exactly the same values as in the display. Now let's see what happens when we unplug it. Well, as expected, power goes down. It already goes down to 0.2 amps, 2 watts. So power consumption definitely goes down. Well, we have successfully concluded this project by creating a portable, non-invasive project that would help us measure energy consumption around the house, display it on an LCD display, and on a dashboard and a server. I hope this helps. This will help us identify electrical consumption issues, tackle them later. As recommendation, we have that these can be compacted by using a PCB board, as you can see in the picture on top, using 3D printer to create a box that is more concise and compact, I would say, so we can move it around the house and place it in the strategic places around the house to measure power and energy. Okay, so this has been all. Thank you so much for your time. If you have any questions, please leave them in the comment.